students, myself JV and Dr. Kiran Yadav. In this session, I will discuss about the postulates of quantum mechanics. Quantum mechanics is based on a set of postulates or fundamental hypotheses. The first two postulates establish the role of wave function in quantum mechanics. The third postulate establishes a connection between each mechanical variable and a mathematical operator. The fourth postulate provides the means to obtain information about the values of mechanical variables. The fifth postulate concerns the determination of the state of a system by experimental measurements. So let's start with the first two postulates of quantum mechanics. The Schrödinger equation does not provide a complete theory of quantum mechanics. Schrödinger, Heisenberg, and others devise several postulates or fundamental assumptions that form a consistent logical foundation for non-relativistic quantum mechanics. In any theory based on postulates, the validity of the postulate is tested by comparing the consequences of the postulates with experimental fact. The postulates of quantum mechanics do pass this test. First postulate is all information that can be obtained about the state of a mechanical system is contained in the wave function psi, which is a continuous, finite and single-valued function of time and of the coordinates of the particles of the system. This postulate implies that there is a one-to-one relationship between the state of the system and a wave function. That is, each possible state corresponds to one wave function and each possible wave function corresponds to one state. The terms state function and wave function are often used interchangeably. Information about values of mechanical variables such as energy and momentum must be obtained from the wave function instead of from values of coordinates and velocities as in classical mechanics. The fourth postulate will provide the method for obtaining this information. Now the second postulate is the wave function psi obeys the time-dependent Schrödinger equation. So this is the Schrödinger equation and it's obeyed by the wave function psi. So we can write it as h cap psi is equals to iota h cross del psi by del t. Here the term in RHS depends upon time, so this is a time-dependent Schrödinger equation where h is the Hamiltonian operator of the system. The time-independent Schrödinger equation can be derived from the time-dependent Schrödinger equation by assuming that the wave function is a product of a coordinate vector and a time vector. So we can write psi qt is equals to psi q and neta t. Psi depends basically on both coordinates and time, so we can separate the part of psi which depends upon coordinates and we write it as psi q, and the time dependent part is written as neta t, where q stands for all the coordinates of the particles in the system and where the coordinate wave function psi satisfies the time independent Schrödinger equation. Not all wave function consist of the two vectors in equation, but all wave function must obey the time-dependent Schrödinger equation. The third postulate is about mathematical operators and mechanical variables. The time-independent Schrödinger equation determines the energy eigenvalues for a given system. These eigenvalues are the possible values that the energy of the system can take on. The third and fourth postulate must be used to obtain the possible values of other mechanical variables such as the momentum and the angular momentum. The third postulate is there is a linear Hermitian mathematical operator. It one-to-one corresponds with every mechanical variable. This postulate states that for each operation, there is one and only one variable, and for each variable, there is one and only one mathematical mathematical operator. A mathematical operator is a symbol that stands for performing one or more mathematical operations. When the symbol for an operator is written to the left of the symbol for a function, the operation is said to be applied to that function. For example, d by dx is a derivative operator standing for differentiation of the function with respect to x. C is a multiplication operator standing for multiplication of the function by the constant c. Hx is also a multiplication operator standing for multiplication by the function hx. Denote an operator by a letter. With a caret over it. The result of operating on a function with an operator is another function. If a is operator and f is a function and we operate a on f, then we obtain g of q, where g is another function. The symbol q is an abbreviation for whatever independent variables f and g depend on. Shows an example of a function fx is equals to log of x and the function gx is equals to 1 by x. That results when the operator d by dx is applied to ln of x. This is the graph of a function fx. Our function is fx is equals to log of x and the differentiation of log of x is 1 upon x. So the lower graph is of 1 upon x. Now let's discuss about the Hermitian operator. Hermitian operators have several important properties. Hermitian operators are linear. Second is, two Hermitian operators are not required to commute with each other. Third is, a Hermitian operator has a set of eigenfunctions and eigenvalues. Fourth is, the eigenvalues of a Hermitian operator are real. Fifth is, two eigenfunctions of a Hermitian operator with different eigenvalues are orthogonal to each other. Sixth is, two commuting Hermitian operator can have a set of common eigenfunctions. Seventh is, the set of eigenfunctions of a Hermitian operator form a complete set for expansions of functions obeying the same boundary conditions. The fourth postulate of quantum mechanics deals with expectation value. So, the first postulate of quantum mechanics asserts that the wave function of a system contains all available information about the values of mechanical variables for all the state corresponding to the wave function. The third postulate provides a mathematical operator for each mechanical variable. The fourth postulate provides the mathematical procedure for obtaining the available information. If a mechanical variable A is measured without experimental error, the only possible outcomes of the measurement are the eigenvalues of the operator A that corresponds to A. The expectation values for the error-free measurement of a mechanical variable A, if given by the formula, then expectation value of A is written as integration psi star a cap psi dq divided by integration psi star psi dq, where A is the operator corresponding to the variable A and psi is equals to psi qt is the wave function corresponding to the state of the system at the time of measurement. Fifth postulate is about measurement and the determination of the state of a system. The fifth and final postulate gives information about the state of a system following a measurement. It states that immediately after an error-free measurement of the mechanical variable A, in which the outcome was the eigenvalue Aj, the state of the system corresponds to a wave function that is an eigenfunction of A with eigenvalue equal to Aj. This postulate says very little about the state of the system prior to a single measurement of the variable A, because the act of measurement can change the state of the system. To understand physically how a measurement can change the state of a system, Consider the determination of the position of a particle by the scattering of electromagnetic radiation. When an airplane reflects a radar wave, the effect on the airplane is negligible because of the large mass of the airplane. When an object of small mass, such as an electron, scatters ultraviolet light or X-rays, the effect is not negligible. So these were the 5 postulates of quantum mechanics, which are very important, and one should know these postulates before studying the quantum mechanics. So that's all for this session. Thank you.